Hello everyone, I am Swarnalatha, working as Assistant Professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss about the cross power spectral density and then the properties of the cross power spectral density. In the previous lecture, already we have seen the power spectral density and the properties of power spectral density. So the power spectral density is confined to a specific random process, a single random process x of t, whereas the cross power spectral density is confined to the power, how the power has been distributed with respect to the frequency of two signals. There is a difference between the auto power spectral density and the cross power spectral density. So first of all, the power spectral density is nothing but how the power has been distributed with respect to the frequency. That is called as what? Power spectral density. Now, what is a cross power spectral density? The cross power spectral density is nothing but it is a statistical property of a random signal. It is a statistical property of a random signal and it gives how the power has been distributed across the spectrum. Here, spectrum is nothing but what? Frequency. With respect to the frequency, how the power has been distributed of two signals is nothing but what? Cross power spectral density. And it is a function of frequency. The auto correlation function, cross correlation function are the function of what? The time as well as the time difference. Whereas the power spectral density is a function of the frequency. And this cross spectral power spectral density is used to determine the influence of a signal in relation to the another signal. How the power has been varied with respect to the another signal has been measured by using the cross power spectral density. Now, we have seen the Wiener-Kinchen relation in the previous lecture. The Wiener-Kinchen relation states that the relation between the auto correlation function and the auto power spectral density. So, the relation states that the auto power spectral density as well as the auto correlation both form a Fourier transform pair. And similarly, the cross correlation function as well as the cross power spectral density both form a Fourier transform pair. So, what do you mean by Fourier transform pair? That is nothing but what? The time average of the cross correlation function of two random processes x of t and y of t is the cross power spectral density, or else you can write it as the inverse Fourier transform of the cross power spectral density gives the cross correlation function. That is called as what? The Fourier transform pair. So, which forms the Fourier transform pair? The cross correlation function as well as the cross power spectral density. And the main difference between the cross power spectral density and the auto cross power spectral density is the auto cross power spectral density. So, you have to consider a single random process, whereas for cross power spectral density, you have to consider two different random processes. Two different random processes you have to consider. And the auto power spectral density, you have to consider what? You are discussing the how the power has been distributed of this random process x of t with respect to frequency. That gives the auto power spectral density, whereas the cross power spectral density gives how the power has been distributed of the two signals, nothing but x of t and y of t with respect to the frequency is nothing but what? Cross power spectral density. And the auto power spectral density is nothing but you are represented by the symbol S. And the auto power spectral density is simply called as what? Power spectral density also, which has been represented by what? XX. So, XX indicates what? Of the same signal only. And I told you that the power spectral density is a function of what? Frequency. Here, omega represents the angular frequency. Then nothing but 2 pi f. Okay. And similarly, the cross power spectral density of two different random processes x of t and y of t has been denoted by S, xy of. Since it is a function of frequency, I have to write F again, or else I can write down the angular frequency omega also. So these are the representations between of the power spectral density as well as the cross power spectral density. So the first definition of the cross power spectral density is nothing but what? The cross power spectral density of two random process x of t and y of t is nothing but the time average of the cross correlation function. Here what is R indicates relation. XY difference, two different random process. Since they are two different random process, we are calling it as what? Cross correlation. Therefore, the time average of the cross correlation function of two random process is called as what? The cross power spectral density of the two random process x of t and y of t. This is the first definition, or else the cross power spectral density of two random process y of t and x of t is given by the time average of the cross correlation between two random process y of t and x of t also. Now, if you consider the random process, the x of t and y of t are jointly wide and stationary. So, what is the condition for jointly wide and stationary? Two random process x of t and y of t are said to be jointly wide and stationary if they satisfy only two statistical properties are not varying with respect to time. What are the two statistical properties? The first one is the mean and the second one is what? Cross correlation function. So what is the first one? The means of the two random process should be constant, and second condition is the cross correlation function should be a function of only the time difference only. So if you observe here, the cross correlation function of here it is a function of both the time t as well as here tau is a time difference. Whereas in case of the jointly wide and stationary means it should not depend upon the time. So it should be a function of only the time difference only. Therefore, the cross correlation function is depending upon only the time difference only. Now, if the two random process x of t and y of t are jointly wide and stationary, then you can say it as the cross power spectral density of the random process x of t and y of t is given by the Fourier transform of the cross correlation function of the two random process x of t and y of t. Similarly, you can write down the cross power spectral density of the two random process y of t and x of t as the cross correlation between the two random process y of t and x of t. This is a first definition of the cross power spectral density. So, power spectral density is nothing but what? How the power has been distributed with respect to the frequency. If you want to calculate the power, average power, then what you have to do? You have to calculate the area under the power spectral density. Then you'll get the power contained in the two random process x of t and y of t. And the second definition of the cross power spectral density has been derived like this. So you are considering that a random process w of t, which is the sum of two random process x of t and y of t. Now, if you want to calculate the autocorrelation function of the sum of two random process x of t and y of t. The sum of two random process x of t and y of t are represented by w of t. Then what is the autocorrelation function of the random process w of t is nothing but what? Relation is nothing but r. Since I am saying here auto means you have to take that same random process. So RWW of t comma t plus tau is equals to what? E of expectation. Here E represents the expectation. R is, it is also called as the statistical average. So E of the expectation of W of t into W of t plus tau. What is W of t here? X of t plus Y of t. Then what is W of t plus tau? In place of t, just replace by t plus tau. Then you'll obtain the W of t plus tau. Then what can you obtain here? X of t plus tau plus Y of t plus tau. Now multiply these two. Then what can you obtain here? Expectation of x of t into here x of t plus tau plus expectation, because you can write down u of x plus y as u of x plus u of y, or else I can write down the x step also. So plus x of t into y of t plus tau. So x of t into y of t plus tau plus y of t into x of t plus tau plus y of t into y of t plus tau. Now, how can you write down the expectation of x plus y as u of x plus u of y? And similarly, you can write down here also expectation of x of t into x of t plus tau plus expectation of x of t into y of t plus tau plus expectation of y of t into x of t plus tau plus expectation of y of t into y of t plus tau. Now, what do you call the expectation of x of t into x of t plus tau, or the statistical average of x of t and x of t plus tau? We'll call it as what? The autocorrelation function. Since you are taking the same random process, we'll call it as what? Autocorrelation. So, Rxx. So, Rxx of t comma t plus tau plus, and what is expectation of x of t into y of t plus tau? Since it is a statistical average of product of two different random processes, we will call it as what? Cross correlation function. So, Rxy. So, Rxy of t comma t plus tau. And next one is what? Expectation of y of t into x of t plus tau. This is nothing but what? The cross correlation between the random process y of t and x of t. That is nothing but what? Ryx of t comma t plus tau plus expectation of y of t into y of t plus tau. Since it is a relation between the same random process y of t, this is called as what? Autocorrelation function of the random process y of t. Therefore, Ryy. So, Ryy of t comma t plus tau. So, this is what? The autocorrelation function of the sum of the two random process x of t and y of t. Here, what is x of t and y of t? These two are two random process. Now, if I take Fourier transform on both sides, so apply Fourier transform on both sides, then what can you obtain? The Fourier transform of RWW of t comma t plus tau is equals to what? Fourier transform of Rx of t comma t plus tau plus Fourier transform of Ryy of t comma t plus tau plus Fourier transform of Rxy of t comma t plus tau plus Fourier transform of Ryx of t comma t plus tau. Now, so what is the in the last previous lecture we have seen the Wiener relation. What is that relation states that? The relation states that the autocorrelation function and the autocorrelation function and the power spectral density both form a Fourier transform pair. It means the Fourier transform of the autocorrelation function of the random process W of t gives the power spectral density of the random process W of t. That is nothing but what? SWW of omega is equals to, then what is the Fourier transform of Rx of t comma t plus tau? This is the autocorrelation. So, the Fourier transform of autocorrelation gives what? The power spectral density. Since of the same random process, or take the power spectral density for the same random process x of t only. Therefore, it is nothing but Sx of omega plus what is the Fourier transform of the autocorrelation function of the random process y of t gives what? The power spectral density of the random process y of t, which is represented by what? Syy of omega plus the Fourier transform of Rxy of t comma t plus tau. So, this gives what? In the previous definition we have seen, this gives a cross power spectral density. So, Sxy of omega. And similarly, the fourth term, the Fourier transform of the time average of the cross correlation between the random process y of t and x of t gives what? The cross power spectral density of the random process y of t and x of t. That is nothing but what? Syx of omega. Therefore, these two terms are giving what? The cross power spectral density. Now, let us derive the equation for the cross power spectral density. So, already has seen the first definition is what? The cross power spectral density is nothing but Fourier transform of cross correlation. This is the first definition. So, we will go for the second definition to determine the cross power spectral density. In order to derive that, first consider two random process x of t and y of t. So consider two random process x of t and y of t. Then consider two sample function defined. Let us consider x of t is a sample function defined and the random process x of t, and similarly y of t is a sample function defined and the random process y of t. So these two are called as what? Sample functions are time functions. Nothing but they are the members of the random process. Okay. Now these sample functions x of t and y of t both are defined from minus t from minus infinity to infinity. They are defined from what range? From the t range minus infinity to infinity. The entire interval the two sample functions have been defined. Now the existence of Fourier transform is what? For the existence of Fourier transform, the signal should be absolutely integrable. That is nothing but what? Integration minus infinity mod of x of t dt should be what? Less than infinity. So this is the condition for existence of the Fourier transform. So in place of x of t, you can take any other signal also. Similarly, y of t also. But they are defined from minus infinity to infinity. So for that, what you are doing is, so instead of considering the sample functions in the entire interval minus infinity to infinity, consider the sample functions only in the interval minus t to t. Then nothing but what? Xt of t, and let us denote those two signals by what? Xt of t and yt of t. So these are the two sample functions which are the portion of the entire sample functions x of t and y of t. These are defined from minus infinity, whereas xt of t and yt of t are some portion of the sample functions x of t and y of t which are defined from minus t to t. So instead of finding the Fourier transform of x of t and y of t over the entire interval minus infinity, first we'll consider the sample functions only over some finite duration. After that, we'll apply t tends to infinity, so that we'll get the entire power in the random process, the sample functions x of t and y of t. Okay. Now, then what is the Fourier transform of xt of t? Nothing but what? Xt of omega. And similarly, what is the Fourier transform of yt of t? Nothing but yt of omega. What is the Fourier transform will do? It will transform a signal from time domain to frequency domain. Now, what is the cross power contained in the two sample functions x of t, y of t in the interval minus t to t? I am not telling over the entire interval. I am considering only in the interval minus t to t. So, in the interval minus t to t, nothing but they are replaced by xt of t and yt of t. So, this can be written by using the Passwords power relation. So, in the previous lecture, we have seen the Passwords energy relation. After that, we have calculated the power. Or else, you can use the Passwords theorem for power signals. Then, what is that relation? Is nothing but what? So, 1 by 2t integration minus t to infinity xt of t into yt of t dt. So, we want the power in the two sample functions or the interval minus t to t. So, what do you call x of t, y of t in the interval minus t to t? We are representing by xt of t and y of t. Therefore, 1 by 2t integration minus infinity xt of t into yt of t dt. That equals to, what is xt of t and y of t? They are nothing but what? The sample functions only, but they are defined only from minus t to t. So, replace this by what? Minus t to t. So, when t is minus t to t, xt of t is nothing but what? X of t, and yt of t is nothing but what? Y of t. That equals to, this is in the time domain. That equals to what? In the, if you know the frequency characteristics of the two signals, then how do you calculate the average power? By using this Passwords theorem power relation. So, what is that? 1 by 2 pi integration minus infinity xt of omega into xt star of omega into yt of omega by 2t into d omega. So, what is xt of omega? It is a Fourier transform of the signal xt of t, and yt of omega is a Fourier transform of the signal yt of t. And this star indicates a complex conjugate. Complex conjugate nothing but what? For example, if it is a complex number, then what is complex conjugate? Let us say x equals to a plus ib. Then what is x star? Nothing but a minus ib. There is a complex conjugate. Now, the energy contained, this is the energy contained only in the random and the sample functions x of t and y of t over the interval minus t comma t. But you want the energy contained in the entire interval and in the entire random process x of t and y of t. Then what you have to do is, you have to take what? The expectation, that is the first one. If you want the energy, if you want the cross power, not the energy, calculate the power. Power is nothing but you have to divide by the time duration. If you want the energy, this term will not be there. If you want to calculate the power, then the energy by the power duration, nothing but the time period gives what? The power. So therefore, what is our average power contained in the entire random process x of t, y of t? You have to take the expectation. And second one, you have to make limit t tends to infinity. So limit you have to take what? First, you are doing this one. If you want the power in the entire random process x of t and y of t in the interval minus t comma t, what you have to take? You have to take the expectation. Now, what is the expectation of? So, what is the expectation of x of t and y of t? So, if you want the power in the entire random process, what you have to do? You have to take the expectation. So, x of t into y of t. So, what do you call the expectation of x of t and y of t? Then in the word, the cross correlation function. Therefore, you are representing by what? Cross correlation function. And what is the time here? U of x of t into y of t. Then what do you call this as? Rxy of t comma t. Therefore, this is called as what? Rxy of t comma t. That equals to 1 by 2 pi integration minus 1 infinity. If you want this is a power only in the sample functions x of t and y of t. If you want the sample power, if you want the average power in the entire random process x of t and y of t, you have to take the expectation on both sides. Then what you have to take here? Expectation of x t star of omega into y t of omega by 2t. This is a cross power contained only in the interval minus t to t. But I want the cross power in the entire interval minus infinity. Then what you have to do? If you want the average cross power contained in the random process x of t and y of t in the entire interval minus infinity comma infinity. Then what you have to do? You have to apply t tends to infinity. So write down here limit t tends to infinity 1 by 2t integration minus t to t rxy of t comma t dt is equals to what? 1 by 2 pi integration minus infinity. So you have to make what? Limit t tends to infinity. So limit t tends to infinity, expectation of x star of omega into y t of omega by 2t into what you have in d omega. And this function we can define as the cross power spectral density or the cross density spectrum. So nothing but what? S xy of omega. Therefore, what is S xy of omega is equals to what? Limit t tends to infinity, expectation of x star of omega into y t of omega by 2t. So this is a second definition of the cross power spectral density. So what is the first definition we have seen? Definition 1. Sxy of omega is equals to what? Fourier transform of Rxy of tau. This is the first definition. In case of jointly Whiteside stationary, you will write down only function of the time difference only. This is the first definition. And second definition of the cross power spectral density is nothing but what? Limit t tends to infinity, expectation of x star of omega into y of omega by 2t. So you can calculate the cross power spectral density either by using the first definition or else by the second definition also. Then replace this is by what? The cross power spectral density Sxy of omega. Then what is average cross power? Pxy is equals to what? And what do you call limit t tends to infinity 1 by 2t integration minus 2t? So this is called as what? The time average. So this is called as what? The time average function. So what is the time average of which function you are calculating? The cross correlation function Rxy of t comma t. So then what is Pxy is equals to the time average of the cross correlation function of the two random process x of t and y of t is equals to what? 1 by 2 pi, and this can replace it by what? Sxy of omega. So this you can replace it by what? Sxy of omega. Therefore, the average cross power is equals to what? 1 by 2 pi integration minus infinity Sxy of omega d omega. So this is a formula to calculate the average cross power. Or else what is one more formula? The average cross power is equals to what? The time average of the statistical average of the random process x of t and y of t. Or else can call it as what? E of what we call the expectation of x of t and y of t. Nothing but what? The cross correlation function. And what are timings here? T comma t. So this is a one formula to calculate the cross power, the average cross power, or if you know the power spectral density, you can calculate the average cross power contained in the random process x of t and y of t. So these are the two formulae. And in case of x of t and y of t are jointly White's and stationary, then the cross power spectrum is nothing but what? A of. So if we say jointly White's and stationary, it is a function of only the time difference. So what is the time difference here? T minus t, nothing but what? 0. That is nothing but what? Rxy of 0. So this is a formula to calculate the average cross power. So this is in terms of time domain, in terms of cross correlation function, or else in terms of the cross PSD. This is the formula to calculate the cross power contained in the two random process x of t and y of t. And what is this relation states that? The relation states that the average power contained in the two random process x of t and y of t can be obtained by taking the area under the density function under the cross power spectral density function Sxy of omega, and it will be multiplied by what? 1 by 2 pi. And this is similarly, what is a total cross power? Nothing but what? Pxy plus Pyx. What is Pxy? Nothing but 1 by 2 pi integration minus infinity Sxy of omega d omega. Then what is Pyx? Nothing but the average cross power contained in the random process y of t and x of t is nothing but what? 1 by 2 pi integration minus infinity Syx of omega d omega. So what is Syx of omega? It's nothing but what? Limit t tends to infinity expectation of, yes, sorry, I didn't find here. So expectation of yt star of omega into xt of omega by 2t. This is what? The cross power spectral density of the random process y of t and x of t. And if the two random process x of t and y of t are orthogonal, then what is the power contained in the two random process is equals to 0. Why it is 0? Because if the two random processes are orthogonal, then what is the correlation? Cross correlation is 0. If the cross correlation is 0, what is the power is equals to 0. That's why if two random processes x of t and y of t are orthogonal, then the average power contained in the two random processes is equals to 0. Now we have finished the definition of the cross power spectral density, how to calculate the power spectral density, and then how to calculate the average cross power contained in the two random processes x of t and y of t. Next, let us move to the properties of cross power density spectrum. So first, we consider the two random processes x of t and y of t are the real random process. The first property states that the cross power spectral density Sxy of omega is equals to Syx of minus omega, that equals to what? Syx star of omega. Nothing but what? It is a complex conjugate of the cross power spectral density of the random process y of t and x of t. It means but we have seen the properties of the power spectral density in the previous lecture. The first property there states that it is the power spectral density is an even function of omega, but here the cross power spectral density may not be even function. Now, in order to prove this, so first you'll see what is xt of omega is nothing but what? Fourier transform of x of t over the interval minus t comma t. Then what is x t of omega equals to integration minus t to t x of t into e power minus j omega t dt. Then if you take the complex conjugate for this, then what can you obtain? So it is complex conjugate of x star of t. Since I are considering that it is a real random process for real value. For example, if a is real, then what is complex conjugate is also the same value only. Since you are considering that x of t is a real function, then what is the complex conjugate of x star of t? Nothing but x of t only. And what is the complex conjugate of e power minus j omega t is what? E power j omega t. That is nothing but what? How can I write e power j omega t as? So integration minus t to t x of t into e power minus j minus omega t dt. What is x t of omega? So integration minus t to t x of t into e power minus j omega t dt. But in place of omega, now we are having minus omega. Then what can I write it as? X t of minus omega. Now, so what is a cross power spectral density? Yes, yx of omega is nothing but what? Expectation of limit t tends to infinity. So it is limit t tends to infinity expectation of yt star of omega into xt of omega by 2t. Here star indicates the complex conjugate. Now replace omega by minus omega. Then what can I write down the cross PSD? So limit t tends to infinity expectation of, so wherever omega is there, so replace it by minus omega. So yt star of minus omega into xt of minus omega by 2t. Now, and in the similar manner, you can write down for what is xt star of omega is nothing but xt of minus omega. And similarly, what is yt star of omega is nothing but what? Yt of minus omega. And what is yt star of minus omega? Replace omega by minus omega. Then what can you obtain here? Yt of omega. Therefore, what is the complex conjugate of yt of minus omega is nothing but what? Yt of omega. Then what is xt of minus omega is nothing but what? X star of omega. Then what is the function limit t tends to infinity expectation of x star of omega into yt of omega? This is called as what? The cross power spectral density of the random process x of t and y of t. X of t and y of t. Therefore, what is syx of minus omega equals to what? Yes, xy of omega. So, what is syx of minus omega equals to what? Sxy of omega. And similarly, you can write down what is syx of minus omega is nothing but what? Syx complex conjugate of syx of omega only. So, take the complex conjugate on both sides. Then what can you obtain? What is expectation of yt of minus omega nothing but yt of omega. And what is the xt star of minus omega nothing but what? Xt omega star. Therefore, nothing but what? Syx of omega star. So, like that, you can prove the first property of the cross power spectral density. It means it may be real or it may be not real function of omega. But the power spectral density is a real function of omega, and the cross power spectral density may be real function of omega or may not be real function of omega, even function of omega. And the second property of the cross PSD indicates the real part of the cross power spectral density of Sxy of omega, and similarly the real part of Syx of omega are the even functions. Now, how do you prove this? What is the condition for even signal? For example, if x of t is an even signal, then what is the condition? X of t equals to what? X of minus t, then it is called as what? Even function. Now, how do you prove this? So, first, what is Sxy of omega from the first definition? What is the first definition of the cross power spectral density? The cross correlation function and the cross power spectral density both form a Fourier transform pair. That is the first definition. So, previously we have seen the second definition and it is the first definition of the cross PSD. So, Fourier transform of the cross correlation function of the random process x of t and y of t. If you consider they are the jointly voids and stationary, then there will be a function of only the time difference only. Then, what is the Fourier transform formula? Integration minus 1 infinity rxy of tau into e power minus j omega tau d tau. Now, how can you write e power minus j theta as cos theta minus j sin theta. And similarly here, integration minus infinity rxy of tau into cos omega tau minus j sin omega tau into d tau. That equals to what? Now you separate the real part and imaginary part. Then how can you write down this as integration minus infinity rxy of tau cos omega tau d tau minus integration minus infinity. Bring this j to the outside. It is a complex value, imaginary value. So integration minus j minus infinity rxy of tau into sin omega tau d tau. So what do you call this as? This is a real part of sxy of omega. And what do you call this as? This is a imaginary part of sxy of omega. Now, what is the real part of sxy of omega? Is nothing but what? Real part of sxy of omega is equals to what? Integration minus infinity rxy of tau into cos omega tau d tau. Now, replace omega by minus omega. Then what can you obtain here? sxy of minus omega is equals to what? Integration minus infinity rxy of tau into cos of minus omega tau d tau. What is cos of minus theta? Is cos theta itself. Therefore, there is nothing but what? Integration minus infinity rxy of tau into cos omega tau d tau only. Therefore, what can you prove that? You can prove that the real part of the cross power spectral density is an even function of omega. That is nothing but what? Real part of sxy of minus omega is nothing but what? The real part of sxy of omega only. That you have to prove. In the similar manner, you can prove for the real part of the cross power spectral density of the random process y of t and x of t also an even function of omega. And third property states that the imaginary part of the cross power spectral density of the random process x of t and y of t, and similarly y of t and x of t are odd functions of omega. That is nothing but what you have to prove. What is the condition for odd signal? So if x of minus t equals to minus x of t, then it is called as what? Odd signal or asymmetric signal. And similarly here, odd functions of omega means the imaginary part of sxy of minus omega is equals to what? You have to get minus the imaginary part of sxy of omega. And similarly, the imaginary part of syx of minus omega is equals to what? Minus imaginary part of the cross power spectral density of the random process y of t and x of t. So this you have to prove. So already you have written in the previous property. So what is a imaginary part of sxy of omega? Nothing but what? Minus integration minus infinity. So imaginary part nothing but the complex part. So minus integration infinity rxy of tau sin omega tau d tau. Therefore, so what is the imaginary part of sxy of omega is nothing but what? Minus integration minus infinity rxy of tau sin omega tau d tau. Now replace omega by minus omega. Then what can you obtain? Imaginary part of sxy of minus omega is equals to in minus integration infinity rxy of tau. Wherever omega is there, replace it by minus omega. So sin of minus omega tau d tau. Now what is sin of minus theta? So sin of minus theta equals to minus sin theta. Therefore what can I write down here? Integration minus infinity rxy of tau into sin omega tau d tau. Because minus sin of minus omega tau is minus sin omega tau. So minus into minus will get plus. Therefore, the imaginary part of sxy of minus omega is equals to what? And what is imaginary part of sxy of omega? Minus of this one. Nothing but what? Minus from this equation you can write down here. So sxy of, imaginary part of imaginary part of Sxy of omega. So this is nothing but what? Imaginary part of Sxy of minus omega is equals to minus of imaginary part of Sxy of omega. Therefore, you can say that the imaginary part of the cross power spectral density form is an odd function of omega. And in similar manner, you can prove for the cross power spectral density of the random process y of x, y of t and x of t. In place of xy, you'll get what? Here yx. That's it. And the fourth property of the cross PSD states that if the two random process x of t and y of t are orthogonal, then the cross power spectral density is equals to 0. Now, how do you prove this property? What is the definition we have seen? The relation between the cross correlation and cross PSD is the cross correlation function and the cross PSD form a Fourier transform pair. Now, in case of the two random process x of t and y of t are orthogonal, if two random processes are orthogonal, then what is the cross correlation function is 0. Then what is the time average of 0 equals to 0. Therefore, what is the cross power spectral density is equals to here 0. What is the Fourier transform of a of 0? Nothing but Fourier transform 0 equals to 0. Therefore, what is the cross power spectral density is equals to 0. Therefore, if the two random processes x of t and y of t are orthogonal, then their cross power spectral densities are 0. And the fifth property states that if two random processes x of t and y of t are uncorrelated and have constant mean x bar and y bar, then the cross power spectral density is equals to 2 pi into x bar into y bar into del of omega. Now, how do you prove this? So, what is the relation between the cross correlation function and the cross power spectral density is both form a Fourier transform pair. Now, the Fourier transform of so what is Sxy of omega is equals to what? The Fourier transform of a of Rxy of t comma t plus tau. That equals to what? Fourier transform of a of, so what is Rxy of t comma t plus tau? It is a cross correlation function, that is nothing but e of x of t into y of t plus tau. That equals to, so Fourier transform of, so a of, so what they have given the condition, they are given that they are uncorrelated. If they are uncorrelated means what is e of x of t into e of y of t plus tau? Nothing but what? E of x of t into e of y of t plus tau, because they have given that they are uncorrelated. So equals to what? Fourier transform of a of, and what is the means of the random process? They have given that they have the constant mean. Therefore, x bar, they are not depending upon the t, they have the constant mean. So for all the values of t, the mean is constant only. So x bar into y bar. Since x bar and y bar are constants, then what can I write here? Fourier transform of x bar into y bar into time average of 1. What is the time average of 1 is nothing but 1 only. That equals to what? Fourier transform of x bar into y bar. So if we can bring x bar, y bar outside because they are constant. So Fourier transform of 1. So what is the Fourier transform of 1? Nothing but what? 2 pi into del of omega. So what can I write down here? X bar into y bar into Fourier transform of 1 is what? 2 pi into del of omega. Therefore, if two random processes x of t and y of t are uncorrelated and have constant mean, then the cross power spectral density is equals to what? 2 pi into x bar into y bar into del of omega. Here, what is del of omega is nothing but it is a impulse function. How the impulse function has been defined? Del of omega equals to 1 at omega equals to 0 and 0 otherwise. So this is the definition of the impulse function. So we'll see some of the examples on this cross power spectral density. So here let us consider two random processes x of t and y of t which are jointly white and stationary, and the cross power spectral density of the two random processes have been given by Sxy of omega equals to a plus j b omega by w for what values of omega? When omega is minus w to w and 0 otherwise. So what you have to calculate? You have to calculate the cross correlation function. You have to calculate the cross correlation function. Now, what is the cross correlation function? What is the relation between the power spectral density and the cross correlation function? Both form a Fourier transform pair. The Fourier transform of cross correlation is the cross PSD, and similarly, the inverse Fourier transform of the cross PSD gives what? The cross correlation function. Therefore, how do you calculate this one? The cross correlation by taking what? The inverse Fourier transform of Sxy of omega. So then what is inverse Fourier transform formula? 1 by 2 pi integration minus infinity, 1 by 2 pi integration minus infinity Sxy of omega into e power j omega tau d omega. Now what is Sxy of omega? In the given problem they are given, when omega is minus w to w, it is a plus a b omega by w. Now we substitute and then calculate. Then what is the cross correlation function we got? Rxy of tau equals to a by pi tau sin omega sin w tau plus b by pi t into cos of w tau minus b by pi w tau square into sin w tau. And one more example is, if two random processes x of t and y of t are jointly wide and stationary, and the corresponding the cross power spectral density has been given by 8 by alpha plus j omega cube, where alpha is greater than 0. So, calculate the cross correlation function. How do you calculate the cross correlation function? The cross correlation function have been calculated by taking the inverse Fourier transform of the cross power spectral density. So, what is a Fourier transform of what the cross PS they are given as 8 by alpha plus j omega whole cube. And you know the Fourier transform of the some standard functions. So what is the Fourier transform of u of tau into tau square into e power minus alpha tau? Nothing but what? 2 by alpha plus j omega cube. Now we compare these two. Compare this Sxy of omega with this Fourier transform of the standard signal u of tau into tau square into e power minus alpha tau. Now what you have here? So you are having here 4 into, in place of 2 you are having 8. So how can you write down 8 as? You can write as 4. So 4 into 2 by alpha plus j omega whole cube. Now it's nothing but what? Now multiply with 4 on both sides. Then what can you obtain here? Here. So you can write down here what is Rxy of tau is equals to 4 into e of tau into tau square into e power minus alpha tau, because the inverse Fourier transform of 2 by alpha plus j omega cube is what? U of tau into tau square into e power minus alpha tau. So if you want here, in place of 2 you have 8 here. So multiply with 4 on both sides. Then what is inverse Fourier transform of 8 by alpha plus j omega cube? That is nothing but what? 4 into u of tau into tau square into e power minus alpha tau. Then what is your xy of tau is nothing but what? Inverse Fourier transform of what is Sxy of omega? 8 by alpha plus j omega cube. That equals to what? 4 into u of tau into tau square into e power minus alpha tau. So like that you can calculate the cross correlation function if the cross PSD has been given, and similarly if the cross power spectral density has been given, you can calculate the cross power spectral density. And if they give the random process x of t and y of t and the cross correlation, then you can calculate the average power also. So therefore in today's lecture we have done with the definition of the cross power spectral density, and then we have seen the properties of the cross correlation function. After that we have moved through the examples on the cross power spectral density. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.